What we have calculated is the changes in entropy of the system. Because if you will recall, the system is what we are interested in measuring. So positive 20 is the entropy change for the system, the hydrogen, the chlorine, and the HCl. It does not tell us about the surroundings. If it were enthalpy, if this system absorbed 20 kilojoules of heat, then we would know the surroundings lost 20 kilojoules of heat, because that's how enthalpy works, and that's the first law of thermodynamics. That is not how entropy works. Just because the system is absorbing 20 joules of entropy, of disorder, that does not necessarily mean that the surroundings is becoming more ordered. Okay? Here's why. If we consider ice melting again, we know that the delta S of this system is positive, because we know ice going to make water is becoming more disordered. What do we know about the surroundings? Well, in order for ice to melt, don't we know that it has to absorb heat? So then doesn't that mean that the surroundings are cooling off? And if the surroundings are cooling off, that means they're becoming more ordered, so the delta S of the surroundings is going to be negative for that process. Okay? And we know that would be spontaneous. But what if we consider hot water cooling off? What's happening to the system? It's getting more ordered, so it's negative. What's happening to the surroundings? Not always. But what if I told you, for example, told you that process is exothermic? If you know it's exothermic, then do you know what the entropy change of the surroundings would be? If it's exothermic, it's giving off heat. So what would the entropy change of the surroundings be? Negative. It would be negative. Huh? If it's giving off heat, the entropy change of the surroundings is going to be negative because they're warming up. They're becoming... Be positive. Thank you. Okay, yeah. If it's giving off heat, the surroundings are warming up, so the entropy change of the surroundings would be positive. But in this case, the entropy change of the system is also positive. So you can't always have, if the system's positive, that doesn't just define the surroundings as negative. If the system's negative, that doesn't necessarily define the surroundings as positive. You can have both of them being positive. You will never have both of them being negative. They can never, both the system and the surroundings will never both be negative. Why is that? The overall change, when I look at the delta S of the system and I add that to the delta S of the surroundings, what that actually gives me is the delta S of the universe. It's the delta S of the universe that actually determines spontaneity. The second law of thermodynamics
States that explains why a reaction will be spontaneous in a certain direction. And entropy cannot. Entropy is not conserved.
Yes, that for a reaction to be spontaneous, as written, the delta S of the universe must be positive. Therefore, they cannot, the system and the surroundings cannot both be negative. The delta S of the universe has to be positive. That is the second law of thermodynamics. Y'all, delta S being positive, what does that say? That says that the universe is constantly moving towards disorder. Because that's what a positive S is, that we're constantly moving towards disorder. So, can I flip back to the previous slide for a second? In this first case where we said the system's positive and the surroundings negative, in order for that to be a spontaneous process, the positive delta S of the system has got to be more than the negative delta S of the surroundings. Okay, so they don't have to be the same value. They don't have to be opposite signs. Same here. On the second one, the surroundings has got to be more positive than the system is negative. On the bottom one, it doesn't matter because they're both positive. That's going to be a spontaneous process.